In our previous video, we delved into the transformative power of discrete compounding, where interest payments accumulate over time, much like a snowball gaining size as it rolls down a hill. Each phase of this process mirrored an interest payment, showcasing how small sums can grow into significant wealth. Now, in our next installment, focusing on value growth, we shift our focus to continuous compounding. This process, akin to the perpetual increase in size of a snowball rolling downhill, will be explored to illustrate the seamless and continuous growth of investments. In the upcoming 10 minutes, you will gain valuable insight into the intricacies of continuously predicting and analyzing investment values as they evolve over time. Through a concrete example that illustrates these concepts in action, you'll discover how this fundamental aspect of finance underpins the strategies of financial institutions worldwide, empowering them to accurately assess the worth of their investments. By mastering this concept and understanding its practical implications, you'll gain a powerful tool for crafting a more informed financial future. This knowledge will enable you to plan and navigate your financial journey with greater effectiveness and confidence. Continuous compound interest involves paying smaller interest amounts at more frequent intervals, leading to an increase in the number of compounding periods. In contrast to the discrete compounding we previously explored, where interest was paid once daily, imagine if interest were compounded every 6 hours. Instead of receiving a single large interest payment at the end of each day, you would receive multiple smaller amounts throughout the day. To illustrate this, imagine a bar graph representing discrete compounding, with a red bar indicating the interest paid at the end of each day. Now, visualize a smooth function passing through the left corner of the discrete bar, with the distance from the discrete bar to the function colored to represent the incremental increase in compound interest during continuous compounding. This visualization highlights how continuous compounding results in a smoother and more continuous growth of wealth over time. The usefulness of continuous compounding is obvious. For financial planning, continuous compounding demonstrates how even small savings can grow significantly over time, motivating individuals to start saving early and regularly. Understanding loans, continuous compounding highlights the importance of paying off loans quickly to minimize total interest payments and debt accumulation. Investment opportunities. Continuous compounding showcases how investments can grow exponentially over time, encouraging individuals to explore different investment options and start investing early. Mathematical concepts. Continuous compounding provides a real-world application of exponential growth, making abstract mathematical concepts more relatable and understandable. Future career paths. Understanding continuous compounding opens doors to careers in finance and economics, where it's essential for financial planning, investment analysis, and economic forecasting. The vocabulary is the same as in discrete compounding: present value, future value, and interest rate. To understand continuous compounding, let's analyze various savings plans with the same annual interest rate, but with different compounding frequencies. Consider several savings plans, each with a promised guaranteed return. Which option would you select? 100% annual interest compounded annually, semi-annually, quarterly, or daily? So let F sub t be the future value of the initial investment at time t. Here, t equals 1 for 1 year. PV, present value, is the value of the initial investment. R, the annual interest rate, and it's usually between 0 and 1. M is the number of interest payments per year. These will vary for each calculation. And T is the number of annual payments. Here it's 1. Then F sub t equals PV times 1 plus r divided by m raised to mt. 100% annual interest compounded yearly. If you invest in this plan, by the end of year 1, you will have the present value of your investment times 1 plus 1 divided by 1 to the power of 1 times 1. This equals the present value times 2 to the first power, which is 2. And so your initial investment doubles after 1 year of 100% interest. This is the same outcome as in our previous video on discrete compounding. Now, 100% annual interest compounded semi-annually, or twice a year. Here, r is still equal to 1, but m equals 2, since interest is compounded or paid semi-annually. So the future value of the initial investment in year 1 equals PV times 1 plus 1 divided by 2, or 50%, to the power of 2 times 1, with the 2 indicating the number of interest payments per year at 50%. This equals the present value times 3 halves to the second power, which is 2.25 times present value. And so your initial investment is 2.25 times larger at 100% annual interest compounded every 6 months. 100% annual interest compounded quarterly. Future value is equal to present value times 1 plus 1 divided by 4, 25%, to the power of 4 times 1, with the 4 indicating the number of interest payments per year. This equals present value times 5/4 to the 4th power, which is 2.4414 times present value. And so your initial investment is 2.4414 times larger at 100% annual interest compounded every 3 months. And last, 100% annual interest compounded daily. I think if you can see the pattern, you know that this is going to be the answer. The future value of the initial investment equals present value times 1 plus 1 divided by 365 to the power of 365 times 1, with the 365 indicating the number of interest payments per year. This equals present value times 366 divided by 365 to the 365th power, which is 2.7146 times present value. And so your initial investment is 2.7146 times larger at 1/365th% compounded daily. Therefore, assuming an effective annual interest rate of 100%, my preference lies with option D, since daily compounding yields the highest amount of compound interest. And so in summary, in compound interest, the general formula FV sub t equals PV times 1 plus r over m to the mth power demonstrates continuous compounding, where interest is compounded continuously over time. The special case, f sub n equals PV times 1 plus r to the n, represents discrete compounding, where interest is compounded at fixed intervals. Continuous compounding implies the benefit of more frequent compounding intervals, typically resulting in higher returns on investments. However, the optimal compounding strategy depends on various factors, including the annual interest rate and the compounding frequency. This is why it is necessary to ask questions such as, what is the annual percentage rate, APR? How frequently is the interest compounded, and what effect does this frequency have on the investment's growth potential? And are there any additional fees or charges associated with the investment that could affect its overall returns? And so this highlights the benefit of continuously compounded interest in your life. The key, as alluded to previously, is to save a little each day, because Small money becomes big money with time. Good luck, and thanks for watching.